Okay, back for round 2 of section 11.1. Hopefully this will be shorter. Alright, so we were talking about how to find limits of sequences, and like I said before, a lot of the time a limit of a sequence is very much the same thing as taking the limit of a function as x approaches infinity. Where you start to run into issues, I talked a little bit previously about things of the form -1 to the n. If I had this in my as part of my sequence formula, this doesn't make sense. If I write -1 to the x, that doesn't make sense as a function because I can't, for example, plug in 1/2 for x or 3/4 for x. I can't take a negative number to a fractional power like that. It only makes absolute sense when I have whole numbers for my exponents there. But so that's one issue. A bigger issue, more important issue, is, as we talked about before, factorials. N factorial makes sense if n's a whole number. However, x factorial, like 3.1 factorial, that doesn't make any sense. So x factorial is not a function. That doesn't make any sense. And as we talked about, factorials show up a lot in sequences. So we have to come up with other tricks to try to simplify or manipulate factorials in order to find their limits. So for example, as we saw before, we might see things like limit of n-1 factorial divided by n+1 factorial as n approaches infinity. This is a sort of thing that shows up a lot. But as we talked about, when there are two factorials in a fraction like this, typically the way to deal with it is simple cancellation. So before we can, I can't think about, if I plug in infinity for n, I get infinity factorial divided by infinity factorial. That's indeterminate, infinity over infinity. However, I can't use L'Hopital's rule here because these are not functions of x. I can't take a derivative of a factorial. It doesn't make any sense. So the right way to approach this is to simplify first. So as we said before, we look at this, the bottom, they're both factorials, the bottom is larger, so we think about what extra numbers does this factorial have that this one doesn't. Well, if I start with n+1 and work my way down, the next number would be n. The next number after that in the factorial will be n-1, but that's where I start to get things that are also on the top. So beyond that, I have n-1 factorial, which cancels with the top, leaving me with 1 divided by n+1 times n. Okay. If you like, maybe I should write it this way once. So as you're expanding a factorial, if you did it the whole way, you have n+1 times n, and so on until you got all the way down to times 2 times 1. However, you can stop at any time. So next number would be n-1. I can stop there with the factorial. So n+1 times n-1 factorial. And then at that point, both the top and the bottom have n-1 factorial, which we can then cancel, leaving us with 1 over n+1 times n. Now this, as n grows to infinity, this is 1 divided by infinity, which is 0. Okay. So sometimes if there's more than one factorial, we can try to find cancellations to deal with it so that there's no longer a factorial. Let me look at another type of example. So this one will be a little bit different. Let me write the question. I want to take the limit of 4 to the n divided by n factorial. as n approaches infinity. Right, so I want to take on this limit and figure out what this value is. But this time, I don't have 2 factorials, so I don't really have an opportunity to simplify it, to cancel anything. So instead, let's study the pattern that this sequence is following. So let's write the first few terms. So when n is 1, I get 4 over 1. When n is 2, I get 4 squared over 2 factorial. But what that is 4 over 2 times 4 over 1. 2 factorial is 2 times 1. 4 squared is 4 times 4. Next one, 4 cubed over 3 factorial, could be written like this. The next one, 4 to the 4th over 4 factorial, I could separate out like this as a product of these 4 fractions. Oops. All right, so each step we are multiplying by 1 more fraction. And initially, the new fraction is bigger than 1. So here, 4 over 2, that's 2. So to get the second term, I took the first term and I multiplied it by 2. To get the third term, I took exactly what was already there in the second term and I multiplied by 4/3. So this is going to be bigger than the second term. Multiplying by 4/3 makes it bigger. The fourth term, I took the third term, all this stuff, and multiplied it by 4 over 4, which is 1. So these will be the same value here. However, the next one, 4 to the 5th over 5 factorial, that's going to be all of these here. Let me just, rather than rewrite it again. Everything I already had times an extra 4 on top and a 5 on the bottom. So I took this previous one and multiplied by 4/5. So this one will be smaller than this one. If I keep going, the next one I'm going to be multiplying by 4 over 6. So 4 to the 6th over 6 factorial will be 4 over 6 times this previous one. Let me actually write it out again. 4/5 times 4 to the 4th over 4 factorial. Hopefully that's still reasonably legible. Okay, so to get the sixth one, we took the fifth one and we multiplied by 4 over 6. 4 over 6 is less than 4 over 5. 4 over 5. So this is less than 4 squared over 5 squared. So 4/5 squared times 4 to the 4th over 4 factorial. To get the next one, the seventh term, I'd multiply by 4 over 7. But 4 over 7 is again less than 4 over 5. So what I'm going to get is a pattern. Let me try to fit it over here. In general, from this point on, 4 to the n over n factorial is going to be less than, well, they all share this starting amount, this parentheses here. They all share 4 to the 4th over 4 factorial, but then they have some factor here extra. But it's going to be 4 to the 4th over 4 factorial. And then what goes in front of it, it's going to be some number of 4/5. And let's see what it is. This power here is, we lost 4, so we had 6 minus 4 gave us 2. Here we had 5 minus 4 gave us to the first power. So in general, it's going to be n minus 4 as our exponent. So the pattern is for n at least 5, or really I guess 4. It works here as well. Okay, if I stick that on. Yeah. For n at least 4, this sequence is less than or equal to this. Because at each stage, from this point onward, we're multiplying by something that's less than or equal to 4/5 each step. Okay, so hopefully that made some sense. There's a similar example in the book, I believe, that you can look at. But now let's use this to figure out the answer to our limit. So I don't need this. This is just to establish the pattern. This is the relevant result here. I'm going to leave that. Okay. So let's look at this. On the other hand, we're looking at this sequence here. It's less than this sequence, but it's also greater than 0. Because 4 to the n's positive, n factorial is always positive. So our sequence is trapped between two other sequences. And so if we ask what happens as n approaches infinity, 0 doesn't change. N approaches 0. Whereas this, 4 to the 4th over 4 factorial, that's just a number. 4/5 to the n minus 4, that's a geometric sequence like we talked about previously. And it's a small number, a number less than 1, 4/5, raised to a variable power. As that power approaches infinity, our small number to the infinite power is 0. So this is a number times something that approaches 0. That's going to approach 0. So what that tells us is any sequence that's trapped between these two, since both of the n's approach 0, the thing that's trapped between also has to approach 0. So this is the squeeze theorem. So you have a squeeze theorem for functions. There's also a squeeze theorem for sequences, which says that if a sequence is trapped between two other sequences and these outer two sequences approach the same answer, then whatever's between them has to approach that same number as well. So our sequence limit is 0 because the sequence is trapped between two sequences that approach 0. All right, so just wanted to remind you of the squeeze theorem. Sometimes we didn't have to use that a whole lot in function limits, but with sequences now, factorials or something that we don't have as many tools to deal with, so the squeeze theorem can become relevant for those. Let's talk briefly about monotone sequences. Okay, so these are a few definitions here. The sequence AN is increasing if the terms get bigger the farther out you go. So every step you take, every time you increase n, the term of the sequence gets larger. So a sub n plus 1, I guess is the sequence is increasing. A sub n plus 1 is greater than or equal to a sub n for all n. And it's decreasing if the opposite is true, that a n plus 1 is less than or equal to a n. Actually, let me be a little bit more careful there. It's increasing if it's strictly bigger. It's decreasing if it's strictly smaller. You don't want to have a constant sequence where it's not changing. You don't want to call that increasing or decreasing. So it's decreasing if a sub n plus 1 is less than a sub n for all n. So intuitively, if you graph this, the increasing sequences, the y values are getting larger with each step, decreasing, the y values are getting smaller with each step. Just like with functions. And the word monotone monotone means increasing or decreasing. So it's just a word that covers both possibilities. Now, one small source of confusion is a monotone sequence is either always increasing or always decreasing. It doesn't mean that increasing or decreasing doesn't mean that it could increase for a while, then decrease, then increase again. If it's monotone, it has to be one or the other the whole way. Or at least eventually. Well, I'll get to that later. To be monotone, it has to be increasing always or decreasing always. All right. So we'll come back and talk about that a little bit more in a little bit. A sequence is bounded let's do it in two definitions. Bounded above means there is a number m such that our sequence an is always less than or equal to that number m. So there's a ceiling for our sequence. Our sequence never gets above that ceiling. Bounded below means the same thing for a floor. There is a lowercase m such that an is always greater than or equal to little m for all n. I won't write it down, but if you say a sequence is bounded, it's bounded both above and below. So there's a ceiling and a floor for that sequence. You never get outside of those two. Okay. So what we want to do with this is just mention an important fact called the monotone sequence theorem. All right. So let me say it like this. If a sequence is bounded and monotone, then the limit exists. So you might see this worded slightly different. Every bounded monotone sequence is convergent. It means the same thing. All right, rather than proving it in the interest of time and board space here, let's just argue why this is true by a quick picture here. All right, so if a sequence is bounded, it has a ceiling and a floor. So let me use a different color here. Let's see if this works. My screen, it looks pretty much the same color, but All right, so we've got a ceiling at capital M, and we've got a floor at lowercase m. So if it's bounded, then the sequence has to, every term of the sequence has to be within these two lines. It can't go above this. It can't go below this. Okay, so suppose I've got my first term of the sequence is right there. Now monotone means increasing or decreasing. So suppose it's an increasing sequence. That means as I go on, my y values have to increase. They have to get bigger with each step. And so what has to happen, if I keep going, my y values keep getting bigger in some way. I know I can't go above this line up here. So my only other option is I can't decrease it. Once I decide on increasing, monotone means I have to continue increasing. So the only thing that can happen is my sequence has to level off. So maybe it levels off like this. It might not level off to up here, up to M. It might not get up to the ceiling. It might level off somewhere before that, but it has to level off. If it's going to increase, and if it's bounded above, it has to level off somewhere. And so whatever y value is leveling off towards, that's your limit L. Right? Similarly, if it was decreasing, you'd have the same thing happen because of the floor. If it was decreasing with each step, it'd have to level off somewhere above the floor. Okay, so all we know is in this situation, if we have these bounds and we have monotonicity, that tells us that the sequence has to level off. That's saying that the limit exists. Okay, it doesn't tell us what the limit is. It doesn't help us find the limit so much as just guaranteeing that the limit exists. It has some answer. All right. So that's our theorem. Let's do, how much more do I have in this section? Let's do one example. Okay, let's do this one. Let me be more direct about my question. Use the monotone convergence theorem to show the limit of n squared e to the negative n. This limit as n goes to infinity exists. So this is a little bit of an artificial question. This is a function that we could find the limit using L'Hopital's rule. I want to ignore that just to illustrate how you might use the monotone convergence theorem in a situation where it's something that we can't directly compute. Okay. All right. So let's do it like this. To use the monotone convergence theorem, we have to show two things. It needs to be bounded and monotone. So I have two questions to answer. Is this a monotone sequence, and is it a bounded sequence? It's, I would say, usually easier if we establish it as monotone first. That'll help us figure out that it's also bounded, or it'll help us to try to figure out if it's bounded or not. Bounded can be difficult without other information. Let's do monotone first. For monotone, again, if it's a sequence where it makes sense to replace n with x, as it is here, x squared e to the negative x, that makes sense as a function. Let's call that function f of x. We can show something's monotone by looking at the derivative, because increasing or decreasing for functions is detected by the first derivative. So if I replace n with x, then I can take f prime, I can take the derivative. This would be a product, so that's 2x e to the negative x. Derivative of this would be negative e to the minus x. So the product rule gives us this. Then we can factor out e to the minus x and x. So we factor it. We want to say, is this derivative always positive or always negative? And it doesn't take too much to say that the answer to that in general is no. This derivative could be positive or it could be negative. However, we have to go back and think, we don't actually care about this function. We care about this sequence. Okay, so let's be a little bit more specific. Let's find where is f prime positive and negative. And so let's make a sign chart for f prime. Okay, so we make a sign chart with the number line here. First, figure out where this derivative equals 0. It equals 0 when x is 0. It equals 0 when x is 2 from this factor. E to the minus x is an exponential factor. That can't equal 0. That's always positive. So the only place f prime is 0 is these two numbers, these two x values. And then if we plug in some test values, let's see, when x is negative, this will be positive, this will be positive, this will be negative, so this will be minus. When x is between 0 and 2, this will be positive, positive, positive. When x is bigger than 2, we'll have positive, positive, negative. So there's our sign chart. As a calculus 1 problem, we'd use this sign chart to say f, the function f, is decreasing from minus infinity to 0, it's increasing from 2 to 0, and it's decreasing from 2 to infinity. Right? But for our purposes, we don't care about f. We care about the sequence. And what this tells me is after x is equal to 2, everywhere after x is 2, we have a decreasing function. So, let me don't really need this. So for our sequence only is defined basically for n equals 1 and onward, for natural numbers 1 and onward. But in particular, after that first term, n equals 1, after n equals 2, this function had negative derivative, so it's a decreasing function. So our sequence is essentially decreasing. For n at least 2, n squared e to the minus n is decreasing. So technically it's not always decreasing. From n equals 1 to n equals 2, it may have gotten bigger. But as we'll see, these details like monotone, what we really care about is if the sequence is eventually monotone. So there may be a few terms at the beginning where it's not, but if after some point it starts to become decreasing, it starts to be monotone from that point onward, that's good enough. So back in our picture, if the first step is going up, but then it's downward from that point onward, we don't really care about the first few terms. We can ignore them and see that it's decreasing. The limit doesn't care about what happens initially. So the answer is it's monotone in every way that matters. Okay. So if you use the first derivative to figure out increasing or decreasing, if you can find a place where after that x value it's always negative or it's always positive, that tells you it's monotone enough. It's eventually monotone, so we can use this theorem. All right. Okay, so it's monotone. It's decreasing in particular. So is it bounded? Well, let's think about n squared e to the negative n. This sequence. N squared is always positive. E to the minus n is always positive. So this is bigger than or equal to 0. So there's a lower bound. And really that's all we need. If it's decreasing and bounded below, that means it has a floor, and so it's going to level off. Right. So that's really all I need to make use of the monotone convergence theorem. If I know it's decreasing, I need a lower bound to make it work. If I know it's increasing, I need an upper bound. But if we want both for whatever reason, we could figure out an upper bound by plugging in, I guess, our first two terms. If it's decreasing after n is equal to 2. So if n equals 2, we'd have 4 e to the negative 2. We should also consider n equals 1, because we don't know if it's decreasing between those two. If n equals 1, we have 1 e to the minus 1. Which of these is bigger? I guess it's... on my calculator this time, so 4 over... yeah, this is bigger. So again, I know that this is less than this because this is what we get when n equals 2, and everywhere after n equals 2, I have a decreasing sequence. So the outputs are shrinking. So this is a peak. All right, so we've got bounded. But like I said before, once we had decreasing, I really only need the lower bound. So it's decreasing and bounded below. So therefore, by the monotone convergence theorem, the limit exists. Okay. Again, let me just re-emphasize this. I just want to illustrate this principle in practice. It doesn't help us. I mean, going through these steps doesn't help us find the value of the limit. So I know the answer exists. There is an answer to this limit, but this method doesn't get me to that answer. It just tells me that it has an answer, and it's a finite answer. In this particular example, if I wanted to find the answer to this limit, L'Hopital's rule would work. I didn't ask you to do that though here, so this is all I'm going to do. It'll be important in some instances to show that things work later on, to have this principle to know that there is an answer, where we won't actually need to know what the answer is. Okay. Okay, so like I said, that's it for section 11.1. So I will give you a list of problems. In the editing process, I'll do something fancy where I have the text overlaid. I think I'm capable of doing that. But I'll give you a list of problems as usual. You should practice those problems as if they were practice for a quiz. Sometime this coming week, I will write up a quiz and post on Blackboard for you to attempt on your own. It'll be a participation grade. I'll know if you download it or not. I won't technically know if you actually attempted it, but I'll trust that you will. And then after a few days after that, I will make another video of myself going over the problems from the quiz, so you can see how you understood the problems. And as usual, if you have any questions, you want to see other examples, You can email me your questions or post them in the comments. And at some point, if necessary, I can make an extra video answering those questions. Okay. So that is it for 11.1. We will continue with 11.2 in the next video.